Hey folks, so my earbuds actually died there. So just to quickly finish the thought, I was going to say that this paper was actually quite important because it kind of it helped kickstart a movement to reevaluate how strong evidence is and how to try to reduce the likelihood of papers being published that really aren't have very weak evidence. And there's been mixed results on that. There's been some good, some bad. At the end of the day, when it comes to trying to evaluate papers, what I tend to do these days, at least what I try to do, what I aim to do, is when I see a paper and I see some claim, some causal claim, like glasses make you nerd immunity. The first thing I think of is what's my prior, right? And my prior on that would be maybe it could have reduced it some, but a factor of 2 to 3, down to like 36% chance of actually getting it relative to a relative to someone without glasses. Like that seems pretty extreme. And so rather than being surprising and going, oh, I gotta share this, it's surprising. It's well, now I'm skeptical because it's way outside of where my priors are. And then I go and I dig into the paper if I care enough. A lot of them I just go, I don't care, and I'm just gonna move on and not update my prior significantly because if it's on the news and stuff and everyone's talking about it, it's likely a little bit of an overblown thing. And then I dig into the paper though if I'm really interested, at least skip down to the results and take a look and see, is it strong evidence? Are they actually, if at all possible, if you know any, if you find some good statistical blogs, you can maybe they'll report on it and mention, hey, these are flaws in it. Maybe some of the commenters will talk about the shortcomings of it. And then what you do is you treat everything just Bayesian way, which is you have a prior, you just figure out the data, how strong of evidence is the data, and then you update to your posterior. And for example, on this one with ESP, I started with a pretty strong prior saying it doesn't exist. But I'd keep an open mind if somebody had strong evidence. I look at this and it's not strong evidence at all. And so, here was my prior, and then after reading the paper, there was my prior. It just moved, 0. And that's what you do. And so I feel like that's a pretty good way to do it. I'll show you one at the end of class. So one that really moved my prior a lot is, for example, beforehand, I kind of had the expectation, now granted, I'm not an epidemiologist, but that vaccines were going to be like super effective. Everyone was kind of downplaying, like anything above 50% efficacy is pretty good. So I was saying maybe around 70 plus or minus 10, And then they say, oh, it's over 90% effective or it's 95% effective. And I was like, really? And I looked at the paper and I looked at the graphs and I looked at some of the data analysis and how they did it and all the steps they did ahead of time where they pre-registered. So they said exactly what statistics they were going to look at and what tests they were going to run and models they were going to use. And it seemed all pretty on the up and up. And so and I had a fairly weak prior to begin with, just because it's not like it's my field or anything, and then updated to okay, I believe them. I'll take my posterior as being what they told me. What the data was. The data was much stronger and overwhelmed my priors. So it depends on the field. I'll show you another epidemiological model at the end, which I'm a little bit more mixed on, and I don't quite know how I feel about it. But anyway, um, that's enough about other papers. Let's actually talk about um, some additional modeling techniques that we're going to be using in this class. And so the next thing I want to talk about, and I'm going to hit a little bit on non-identifiability, which is a really important topic. And so we'll talk about that some too. So let's suppose, just to go back to what we've been talking about all this time with different heights of men and women, and it's different heights of, based on weight and stuff. And let's suppose I just wanted to do something very simple, which was compare the heights of men and women in that one data set. So how would I do it? So uh, I've already kind of hinted at it in some of the stuff that we've run up till now, like when I included treatments in the data set. But it's important to actually talk about how you would actually run this sort of model, where you want to figure out the heights of men and women separately, and perhaps also you might want to also get what's the difference in their heights. So you can also do it if you want a condition on weight or on height when you're uh, condition on weight when you're predicting the height or whatnot. But we'll stick with just trying to just do without any linear regression or anything, just a simple compare men and women. So how would you do this? Well, you say that the heights are, yi here, or I'll do hi, is going to be normally distributed about some mu I and some sigma, right? Just like we've always had. Maybe I'll write this in a little bit darker pen here. All right. And then you ask, okay, so mu I, how am I going to write this? Well, this one, you can write a few different ways. So for right now, I'm going to show you the dummy approach, which is not, it's the kind of the most common, and it's actually the default for a lot of statistical programs. But we're not generally going to use this very much. We're usually going to use a different approach. And what you do for the dummy approach is you have, first of all, just some alpha, which is just our basic mean, right? Um, and then what we need to add on to it is a dummy times, or beta times our dummy, which we'll call this like dummy m. And what this thing is that it is a list of data points where it's just say, is male, and then it's just 1, 1, 0, 0, 1. It's just 1 or 0 depending on whether or not the person is male or female. All right. And so we have our full data set of all their weights and heights and ages, and we look at, okay, which one are men and which one are women, right? And that's it. And so now what does that do when we plug in this dummy right here, the end? Well, what's going to happen is this. For all the women, what do we predict? If they're a woman, helps if I can spell, women, what's it going to say is mu I is just equal to alpha plus beta times 0. And so this goes away. So we're going to predict that women are height alpha. So actually, the way to interpret alpha is not the average of the whole population now, but just the average of women. And then for men, what is it? Well, now mu I is going to be equal to alpha plus beta times 1, which is just beta. So the way to interpret this beta is what is the difference between men and women? So what is, on average, how much taller are men than women? That's what this beta means in the case of a dummy. Now, you can do this. I'll actually do an example of this in just a minute, where I'll actually do it in the computer. But I just want to mention that what if we had more than two categories? In the book, I think he gives the example of, let's say you wanted to run a regression on like which house from Harry Potter you were in, or you are, where it's like Gryffindor or Slytherin or whatnot. There you have four. So how do you do dummy variables then? Well, what you have to do is by default, you want to choose a baseline, right? So let's say that that's like Gryffindor or whatever, right? And then what you have is that you have now three columns, which will be is Hufflepuff. I gotta remember all my Harry Potter houses. Let's see if I can remember them all. Hufflepuff, what is it? It's Ravenclaw, I think. Ravenclaw, and then there's Slytherin, right? Is Slytherin, which I'm just gonna do is Slids. There we go. And then for each one of them, you'll also have, there you could also have the is Gryffindor, but you don't need it here, right? If someone's a Ravenclaw, then what you're gonna see is that they're not as Hufflepuff, they're not as Slytherin, they're a Ravenclaw. If they're a Slytherin, you might see a couple Slytherins there, and so all of them are 0 except for the Slytherin one. That one's a 1. Hufflepuff, same business. Now, what about Gryffindor, folks? Well, that one, they're not a Hufflepuff, they're not a Ravenclaw, they're not a Slytherin, right? So it's all zeros. Now, when we go over here, if we wanted to run our regression, where we wanted each one, where we wanted to estimate the mean or the differences or things like that, what we could do is that we set, first of all, one of them as our baseline, which, as I said, in this case, is Gryffindor. And then you could say beta times dummy for Hufflepuff plus beta, we'll call this H, let's say, R times dummy for R, right? Plus beta Slytherin times dummy Slytherin. And now what this does is that if they're, say, a Gryffindor, then mu I is just equal to alpha plus 0, 0, 0, nothing, right? This is for Gryffindor. Oh boy, now I don't know how to say. I think it's Y, I think. I don't know. And then for the Hufflepuffs, it'll end up being UI is equal to alpha plus beta H DH, and so on and so forth, right? Each one will only have one of these be ones and the other ones be zero. And so what happens is now beta H can be interpreted as what's the difference between a somebody from the Gryffindor house for whatever you're measuring, you know, and uh, and how much extra or less is it for this value for on average for a Hufflepuff than for a Gryffindor. So everything is relative to the Gryffindor. So let's just quickly do this example with the men and women. I'm not going to do the Harry Potter house thing. I'm sure you can look it up in the book. I mean, he mentions it in there. But what we'll do is we'll go through it with men and women, and then I'll show you the alternative approach on how to do it rather than using dummy variables, and it'll be the better approach in general. But at least in my opinion. But what will be interesting about it is that we'll have to talk about how you interpret these things. It turns out it's going to make some things interesting when you look at the joint distributions and you combine things, and when we talk about the pros and cons of this stuff. All right. So let's get to it. So, and by the way, I'm going to also, just because I'm already going long on this lecture, I'm going to probably speed things up by having some of the data kind of, I'm just going to copy and paste some of it to make it go faster. So we download the data, which I use the stuff from the cheat sheet, which you guys should have a link to from like last week's lecture or 2 weeks ago or something. I'll probably put it in the description again. We'll see. And then don't forget, we also want to probably select it down to only the ones with ages above, you know, 18 or something like that. Right, I think it does that you do something like that. I'm trying to remember now, suddenly I'm blanking. I think that does it. Let's see. The D, let's take a look. Yeah, 346. Oh, it should be greater than or equal to 18. There you go, 352. That looks correct. So now let's do our model. It's easy enough. Our dummy, well, it's easy, fairly easy, but we do have to be a little bit careful. So we have our dummy model, and we can already put in the ends okay. All right, the last two lines are going to be pretty easy because we already wrote those up, which is the mu's are equal to alpha, and I'm going to call this dummy, this beta. We'll call this like beta male diff or something like that, right? Or male added height, right? I don't know what we want to call it, right? We can come up with a lot of different names. But what we got to do though is we still do have to put our priors on things. So we first of all we have our sigma. I'm going to use the since I'm going to go way back and use the prior that he used in what was this, like beginning of chapter 4, but this is before we even did linear regression. So remember, I probably was complaining about some of it. So for the alpha, it's okay. We can do normal alpha 178.20, right? Because that was like the mean height. Now, of course, this alpha is now interpreted as the average height for a female, which is probably going to be smaller than a male. So we could lower it some, but I'll keep it the same. And same thing with this thing, which I remember I hated the sigma, which was like some uniform from 0 to 50, but I'm going to keep all that, just like he had in the book and early in chapter 4. And now the question is, how about for this male added, this beta for males, right? Maybe I can just call it beta male. Let's do it that way. That's it. And, you know, we know it's the difference. I explained it on the board. We'll just go with this. PM.normal. Well, first of all, we could if we wanted to do a log normal or something, because we know that we expect that the males should be taller than the females, right? Now this is a society which I'm not familiar with, so maybe it's possible that females are taller, but I highly doubt that, right? I mean, you could set it and constrain it to be positive, but I won't, just for the sake of not doing it. And we probably want some sort of a factor. What do we think is kind of a reasonable estimate for how much taller they are? I don't know. Probably within 10 centimeters. How much taller is 10 centimeters? let's see, I got to do my centimeter conversion. 10 centimeters in inches. Actually, it's around 4 inches. So, if they're within like a foot of each other, this thing will pick it up, right? Which I feel like is probably okay. Oh, that's interesting. Yes, I am still using it. I was literally just typing in it like a minute ago. All right. Anyway, so so we have this, and one thing to notice in this, this is actually part of the reason why it's a little bit odd using these dummy variables. And the reason why, a little bit awkward from the Bayesian perspective. So we have this prior on our alpha, and we have this prior on our male. What is our prior for the height of a male? Not the difference, but the overall final height, like average height of a male. What's our prior for that? Right? It's a good question. Well, I would argue, right, before we look at any of the results here, I would argue that with our prior here, where it was beta male, I'm using the wrong one. Well, I used that good one that was like really dark just a moment ago. I think Paul and Ben you all really liked. Beta male was distributed normally about 0, 10, and alpha was distributed normally 178, 20. So what's happening here is that, of course, as we know, the average for the male, if we were to say it like average for male, is always just equal to alpha plus the beta male. So you're adding these two normal distributions together. You're adding two draws from a normal. We're drawing a draw from two different normals and adding them together. These two draws together. And so, what's the distribution of that? Well, you can do the math here. It's not terribly that informative, but when you do it, you add the variance, not the standard deviation. So you add. The way you do it is you have to take like this thing squared plus this thing squared, add them together, take the square root. Kind of like if you're trying to find like the side of like of a triangle, the hypotenuse. So in this case, it's going to be the means are just added together. So our average male our prior is going to be a normal, and it's going to be whatever 10 squared plus 20 squared square root is, right? Which is going to be 500 square root, which is going to be no, that's not right. 100 plus 400 is 500 square root of 500. Yeah, that's right. What is that going to be? 20, I don't know, 23 or something like that. I don't know, 23-ish. I'll put a little question mark there, right? But the point though about it is that you notice that why is it? It seems weird because you would think we would have pretty much the same prior for our men and women, but ultimately because we're saying we're not sure about the women, this is our prior on it, and then we're not sure about how much is to add on together. When you add them together, you're even less sure about the men than you are about the women. It's for sure bigger. I don't know exactly how much. That was my little question mark there. It's probably closer to 22 because 22 is 484, and so it's probably just a little over 22. Now that I think about it, 22 point, I don't know, 1 or something, right? Um, so anyway, the point though is that we're less certain about it than we are with this one. We have a wider prior for men than women, and that doesn't quite seem right. And in fact, whenever you do it, whenever you do this sort of thing with the dummy variables, your base will always end up having the smallest. You'll always be most certain about it in your prior, and you're always less certain in your prior about any of the other categories. And so it's a little bit of an awkward thing. You would prefer if they had like the same priors or something along those lines. And so let's go back to the board though and take a look at this. Back to the computer and take a look. So, sorry, I put these in the wrong order there. There we go. So I already ran it. And now let's just take a look at the results. So we say az.summary, and let me zoom in a bit here because I haven't done that yet. az.summary of the posterior. And we run this, and what we get out, is fairly reasonable. Here's the alpha, 150 thereabouts for women, and then the difference between men and women are about 10 centimeters. So actually, that was pretty good. It's somewhere between around 10 and 12. Okay, right, and you kind of just go, okay, that's interesting enough. Now, what if I was actually curious about the average for men, though? Right? Like, what if I actually want to get the men's value? So one thing that you might think, I'm just going to tell you that this would not be correct, is that you might think, okay, well, in the worst case, in the bottom case of 5.5%, it would be the 148.9 plus around the 9.9, right? The low end of the alpha and the low end of the beta male, you add those together, and you get, 148.9 plus 9.918, and then you get, my 5 percentile might be like 158.8, and then for the upper end, I get 150.18 plus the 11789, right? 787. Because on the high end, you get the high alpha and the high beta male, the high difference. So you add those together, and that gives us our estimate for the male of the 94.5%. You might think that, right? And then, but you would be wrong. All right, I'm just going to say right now, you're wrong. Because you can see right here, the difference between the top and bottom here is about 1.3. And if you do it this way, by the way, it looks like it's something more like 3.1 here for the difference between the 94 and 5.5 for the males. And so you would say, if you did it this way, you would actually end up having that the males you're much less certain about than the women. But it turns out you don't do it this way. You don't just take these sides and you add them together and you try to figure out that way. What you have to remember, talked about this before, and we're going to come back to it right now here, which is that remember when we're doing our solutions for everything, we have all of our parameters. In this case, we have alpha and beta male, and we have sigma. We have those three parameters, and what we ultimately solved for was we said that the probability, remember this is our good old friend Bayes formula, which is doing all the hard work for us. The probability of alpha, beta male, and our sigma, given our data for all of our heights, observed heights, all of our HIs, right? So we can do all of our H's. It has to be proportional to the likelihood, right? Probability of the H given our alpha, beta male, and sigma times our priors for them, right? And so the point, though, is that at the end of the day, once we've solved all this, we have a function here of three variables, right? So at the end of the day, what we're going to end up with is a probability distribution that is a function of three variables, all of our parameters. And in this case, it can be any shape it wants to be, right? Based on wherever this stuff tells it to go, it'll be there. Now, if you just ignore the sigma for the moment, just because I don't care about it, right? This is a two-dimensional function. If you can get rid of it if you integrate it out, blah blah blah, right? But you can look at this 2D function of alpha and beta male, and sometimes that we did it, they were just kind of totally like just totally random, right? But what we're going to see here is that they aren't. They aren't just totally random. So let's quickly make this plot. So this is called the joint distribution because it's not just the distribution of one of the variables, it's the joint of the two. So let's actually plot the joint distribution of alpha and beta male and take a look at what ends up happening with it. You'll see it's not just like that. It's actually a different shape. So here we go. And that's going to affect how we actually get our final estimate for the males. All right. So first of all, let me just do it this way where I do plot posterior just to show you each one of them individually. So posterior of alpha. So I can plot, say, here's the plot for alpha. Right, and this looks pretty cool. Mean was about 150, right? Mean about 150, whatever. That's the, yeah, I guess it rounded there. and 89% between 149 and 150. Yeah, thereabouts. That's pretty good, right? And it draws little arrows there. It looks cool, right? And then similarly, we can do it for the beta male. And there it is, mean 11, blah, blah, blah. So, but now let's actually plot the joint, right? So this is saying, by the way, just to be clear, is that if you took all these and you said for the alpha, you drew like a little line here, right? And I'm sorry, I did it in the same color here, right? How much is inside this little strip? And you keep going along with all the strips. And what you're going to find out is it looks something along these lines, right? Where this is right at the 150 for the alpha. And then it goes, plus or minus 1, right? 149 or whatever it was, right? 151, right? And so most of the data was inside of this strip here. And then, this percentage was outside of each one and blah, 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 right? That's what it's actually doing. And then similarly for the beta, when you plot the beta one, it's like if it sums up going this way, right? Taking strips like this, and then it gets a distribution for it too. And you can plot all of this together with plot joint. And so now we can say az.plot joint, and you say it's the posterior, and then you need to specify right here var names. And you have to say which ones you want to plot together. So in this case, we don't want to include the sigma. We want to do alpha, and we want to do beta male. So we run this, and we'll take a look at the plot here. It looks pretty cool. Here it is. Here's our alpha. Here's our beta male. And then here's those are those posterior distributions again for each one of them. It's exactly what we expected. And so it looks pretty cool. But you'll notice it's not just a normal. It looks correlated. Where if alpha is high, that tells us beta male is low. And when alpha is low, then beta male is high. What's going on here, right? That's kind of weird. But as soon as we think about it, it'll be very intuitive. So let's take a look at it really fast on what's going on here. Suppose, for the sake of argument, that I had actually estimated, rather than estimating the difference and the heights for women and then the difference, I had instead estimated the heights for men and the heights for women just directly, right? And so what would have happened is I would have had my height for women right here, my alpha, and I would have gotten some estimate, which we're still yet to quite figure out, but we will in just a moment, the heights for male. And let's suppose that's, I don't know, about 161 or something like that. And we had some distribution there, right? We aren't quite sure what it is for men. We aren't quite sure what it is for women. But you imagine we kind of just took the data set, split out the women, estimated that, took out the men, estimated that, and we're not sure about it, right? Now, suppose I were to tell you that, okay, out of this one, suppose by chance, we want to know what the difference is, all right? So now we're working backwards. Well, suppose that I say, okay, well, in this case, it turns out, there's some chance that it's really high for women, right? That women are actually really tall, right? I don't quite know the mean, the true average, right? I have some estimate, there's some uncertainty. Maybe it's really 152. If that's the case, how big is the difference? Well, on average, the men, it could be that they're tall, it could be that they're short, they could be in the middle, right? But on average, the distance is going to be a little bit smaller because, this is a high estimate for women. So in this case, the difference is kind of small, right? So whenever women happen to get a high guess, whenever the chances that our estimate for women are high, the difference from it and the men is relatively small compared to when we get an estimate for women that's small. If we say, oh, well, maybe women are actually shorter than we think, than the average from the sample, then in that case, now the difference between men and women on average are going to be pretty big, would be our guess, right? So if we have a small if we think women are shorter, then therefore the difference between them and men must be bigger. And vice versa. If we think women are taller, the difference between them and men is smaller. And so the two are correlated because it just so happens, because it's clear that the difference has to get us to the average height for a man, right? And so you can see how the difference goes in direct opposite as are changing in the estimate for the height of women. So we're uncertain, on average, this is the distance, but sometimes the distance will be smaller, sometimes it'll be bigger, depending on what the estimate is for our women. And that's why what's happening is that when we look over here, anytime that we estimate the height for women to be high, then we say, well, then probably men aren't very much taller, because it turns out that women are on the higher end of what we thought for average height. So that means that men aren't that much taller, and vice versa, right? When women are shorter, there we think that therefore the difference between men and women must be much bigger. All right. So how do we actually get the average height of men? Well, what we do is that for each pair here, right, we already know that alpha plus beta male has to give us the average height of male. So here, for example, for this sample right here, where it was 150.5 and about 9.5, we just take 150.5, add on the 9.5 there, and then we get our estimate for men, which would be around 160. Now we don't ever take, here we go, 150.75 almost, and we don't ever add on one of these y's, that are way up here, because we can see that in our posterior, any of the alphas that are paired that are way up here always have small betas. They don't ever have a large beta to go with them. So you never take a large alpha and add on a large beta. So in general, all that we have to do is just make sure that we keep all the alphas and betas that were sampled together, right? Because if we look at the posterior, what's pretty cool about it is, it gave us all of our samples for alpha. There's a whole bunch of them. And then we also have our posterior for beta here, beta male. And you'll notice that, there's some variance in there, right? But whenever you have a high estimate for the alpha, here's that low estimate for the beta, right? And if we kept printing out more, here's a relatively small estimate for the alpha, and here's a higher estimate for the beta. So all we have to do is take these, keep them lined up, and add them together. Posterior of alpha plus posterior of beta male. And this should give us our estimates for the height of men, right? So men are, we'll call this like alpha men, right? And you can even plot this into, even though it's just like literally just a NumPy array, you can even plot this into summary if you want. It'll give you like a warning or some stuff because like, hey, you don't have all this extra information, you just have the raw number here. And what you'll see here is that actually our range goes from 159.5 up to around 160.9. So it's about a difference of around 1.5 here, versus when we had done it manually incorrectly, we got much larger bounds. Because the reason why was that when we had our much larger bounds there, the way we generated it was we just said, oh, okay, we know the difference is sometimes small and sometimes big based on the distribution of the differences. And we know the height of women is sometimes large and big. So what we did foolishly was we took the upper end of the alpha and we added it to the upper end of the difference. So it was way overshooting. And it was saying, okay, the men's height on the high end is here. On the bottom end, we took the smaller alpha and then we added in the smaller distance. So it was like all the way over here. So we said, oh yeah, men's height are somewhere in this huge region here. When in reality, once we accounted for the fact that high numbers on one correspond to low numbers for the beta and vice versa, they actually were much tighter estimate around the smaller area, around the actual height for the men. Men's height didn't vary nearly as much because of that correlation between average height and the difference of women and the difference. And so it's an interesting result that you have to keep in mind that anytime that you want to get some extra value, because oftentimes in your models, you do not actually estimate one your parameters don't include the thing that you really want, just because sometimes it's easier to estimate things differently or have more complicated models and stuff where you end up wanting to combine parameters at the end. And in this case, here we wanted to combine the difference and the alpha for women into the alpha for men. And to do that, what you always want to do is you want to take the samples and then with those samples calculate the new one. You don't ever do any sort of formulas or anything like that. Just take the raw samples and do the calculations on that. All right. And so you take the raw samples, add them together according to what the formula is. You get your new samples for it, and then you can run it, and everything will work. Because behind the scenes, these all these samples can include the correlations. They can include complex relationships between the different parameters, and it'll all be taken into account when you calculate things. If you try to do it just manually by eye or something like that, it'll always lead you astray. Well, not always lead you astray, but it will frequently lead you astray, I should say. And so you should be careful and just do it manually, right? So this is something called calculating pretty much like a contrast. Well, not exactly. Later on, we'll do a contrast that's almost the same. But typically, contrasts are when you take differences between things to find the differences. So it would be this is the opposite. But anyway, you just find functions of the parameters that you're interested in. You just take the samples, and then that's how you get it. And then you do all your analysis on this. So if you want to, you can do the AZ dot posterior of alpha min. Oh, Harvest has, oh, it's not posterior. We want plot posterior. Sorry. And there it is, average 160. There's the range. It looks just like something that we could have generated from our model, right? And in fact, it does come from our model. It's just that we had to combine some of the stuff together. So now with that done, I want to quickly talk about doing index variables. It only takes a minute to explain them. What you do instead is instead of doing this thing where our prior, where by the way I should mention is that while our prior was wider for the min estimate, we said the actual posterior wasn't very wide at all anyway, so the data swamped that anyway, so it didn't really make a practical difference. And we do this the second way, you'll see that it doesn't really make any difference. So, but you still want it to be, you still want the priors to match up with your beliefs ahead of time. And we had no prior belief that men were actually more uncertain than women, and so you shouldn't try to do that. And so for an index variable, what happens is this. It's very straightforward. All that you want to do is instead of having an alpha and then a beta, we just want two alphas, one for men, one for women, right? So you could do this, I know what you're already thinking, like, I know how to do this. This is easy. We just add we have like an is male, and this is not how you do it, right? And is female, right? We actually add in the last categories, 0, 0, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0. And then we just have alpha 1 times is male, or alpha m times d male, plus alpha female times d female. And you could do this, you could, but this isn't the way we do it. We actually come up with an even slicker way. It's a slicker way of doing it. What you do is this, is you just have a gender, for example, right? You have gender, and you just have zeros or ones corresponding to male or female. Now, if you go to the house example here, you could have instead had something to show you that's actually different here. You'll see how it's very different once we actually do this, where we have house, and then you have like 0, 3, 1, 2, 2, 1, 0. And this corresponds to a Gryffindor, right? This one would be the Slytherin, whereas house number 3, house number 0 is Gryffindor, house number 1 is the Hufflepuff, and then house number 2 are Ravenclaws, right? So here's another Ravenclaw, here's another Hufflepuff, and here's another Gryffindor, right? And so you have a house variable which just gives an index, 0, 1, 2, or 3. It numbers the different houses, all right? And so here, when you only have two genders that listed in the data set, it's just 0 or 1, right? If we had more genders, then we would go up to 0, 1, 2, 3, 4, etc., right? And now what you do is instead of doing this, what you have is you say that the mu I is equal to alpha Now this is where we have to be a little bit, this is where you'll see things are a little bit interesting here. We say gender of I with brackets here. All right. Now what is this saying? Well, what we're going to do is this, is that we're going to have two alphas. We're going to have alpha 0 and alpha 1. Okay? And you read this just like you would read computer code. All right? So let's suppose that we're looking at uh, the 0, 1, 2. I is equal to 2. All right? 0, 1, 2, because we started at 0. So in this case, what is gender? So for mu2, that equals alpha of gender of 2. And so we go, okay, well, what is gender of 2? 0, 1, 2. So now that becomes alpha of 1. Helps if I can actually count this, right? Because gender of 2 is 1, so now that's alpha 1. So for the second person, our estimate for their mean is equal to alpha 1. Meanwhile, for say mu3, then that's going to be alpha gender of 3, and that's going to be alpha 0. So for this guy, we're going to use this alpha. All right. So now we just have a list of alphas that we list. Okay, there's going to be one for every single thing that we want an alpha for. So in the cases of the different Harry Potter house, we'd have an alpha 0, 1, 2, and 3. And then we just look up, okay, do we use alpha 3 for this guy? And for this guy, we use alpha 2. And for this guy, we use alpha 0, just by looking it up in the list. And then we just have to put our priors on them, right? So we just can say alpha, and then you could do this several different ways. It depends on how you want to write it, but the alphas here are all going to be the same prior here, which is going to be 178 and 20. And what you can do is that there's ways in PyMC3 and all the other languages where you can pretty much say, hey, look, for this one, there's not just one of them, but there's two alphas, right? And it'll just set the same prior for both of them. If you wanted to, you could manually set the priors. You say alpha 0 is this and alpha 1 is this, and you can kind of build a list of them. I'm not going to do that right now. Maybe later in the semester we'll do that. But in general, you can just say, okay, all my alphas have the same prior. All right. And this makes it a little bit easier because now if you say, okay, now we have 4 houses here, all the code just stays the same. You don't have to have extra dummies and more parameters and things like that. You just say, okay, rather than 2 of these, there's 4 alphas. And it's fine. It makes a list of 4 alphas and you're good to go. So let's quickly do it this way. It only takes a moment. All right. So let me pull this up. So we're going to be doing the same thing. Here we go. So these are called index variables. So I'm just going to paste it in here just to speed things up. So here's our index model. And you'll see that now I renamed it alphas instead of alpha, just because now there's more than one alpha. And then you'll see right here, I put in a comma shape equals 2. That says, hey, there's 2 alphas. Right? And then down here, I have my sigma, same as before. And for my muse, instead of having alpha plus some beta times the dummy, is now just alphas of bracket d dot male. So remember, d dot male here are 0 1s for whether or not they're a male. And you can already see here, if I said, for example, let me show you this. Let's say that I said, alphas equals, just for the sake of argument, let's make them a list here. Alpha 0, comma, alpha 1, right? So now I have this list of 2 things. I might have to make this a NumPy array. We'll see. I do, probably. Let's see. Yeah, just give me 1 second here. Don't worry, it'll be fine. np.array. There we go. And then you do this, and now look at what we get, right? What happens here is dmale. Oh, that's a lot of them. D.male, we'll just look at the first few here. You have a 10010. And now when we call this code, now we get alpha 1, alpha 0, alpha 0, alpha 1, alpha 0. Exactly that. And so that way now our mu's are going to correspond to the correct alphas, right? Because all this did was make a list of 2 alphas. And now we just say, okay, now fit them. So now if we run this, we should be able to get our answer. So let's see it. So we'll let this run real fast. There we go. We'll plot our posterior, and you're going to see is that the posterior is almost identical, right? I mean, there's some Monte Carlo variation like normal, but it's pretty identical. 159.6, 161, 159.6 thereabout to 160.9, so it's a little bit lower on that end, but more or less the same. Right, and then you can also see, I'm sure if you can compare the means yourselves and such. What if we want to get the differences? Well, once again, now if we want to get this contrast, now I'm actually using the term correctly here, I'm pretty sure, which is that we need to now take the difference between alpha 1 and alpha 0. So how do we do that? Where we take posterior of alphas, and now this is a little bit tricky here, because now that it's alphas, you'll see each one has a pair of values in it. The alpha for the women and the alpha for the men in this guess. There's a few ways you can do this, but let's just suppose for the sake of argument, if I did 1 here, this grabs the first element, the first set of male and female. And then if I grab 1, that's the male versus 0, that's for the females. So what you can do in general is you can put a colon and say, give me all of them. And then the 0 says, give me all the women. And now we can say, give me all the men minus all the women. And these are all of our differences. Diffs. And now we can do az.summary of diffs, and hopefully we'll get something that matches. So the difference is 10.85, and it varies between 9.9 to 11.8. Is that about what we got? 9.9 to 11.8? Pretty darn close. A little bit different just because of variance based on sampling, but pretty darn close. Right, and so we get all these results. If you're really interested in it, you can try plotting the joint distribution. In this case, you can just say, our name is alphas with an S. Here you'll see that this is the distribution for men right here. Here's the distribution for women. And they look pretty uncorrelated, not a surprise, because they pretty much are just separate data that we're estimating them off of. All right. So cool. That was all I want to talk about with dealing with index variables and categorical variables in general. So you typically just want to do this sort of index approach. Now, what I want to get into, we still have 2 more things to go. I know I'm going way over what I actually thought I would. So let's see here. I'll make you a deal. I'll be done within 30 minutes. All right. I'll try to speed things up a little bit. But it turns out that before, when we looked up here, we had this correlated thing. It turns out it can get very extreme sometimes. So right now I'm going to do a model that is pretty tricky. All right. This is a model that will be you're going to look at it and say, can you even fit this? And the answer is yes, we can. We'll fit it just fine. But, well, the computer will not like us doing it. It'll cry a little bit as we do it. But at the end of the day, it'll fit it. It'll be able to sample from it. So suppose I say, okay, we got some data here. We got some X and some Y, X, Y, and we're going to fit a regression. So let me just quickly draw this here. 1, 2, 1, 2. All right, and here's our data. You ready for it? That's our one and only data point. We have one data point, and we need to fit a regression line to this. How do you do it? Right? Well, obviously, it's not going to be easy, right? And normally, if you plot this into a normal, a standard type of algorithm, a non-Bayesian algorithm, it will vomit. It'll just suddenly spit out a bunch of errors. Right? Say, I'm done with this. I can't do this. You only have 1 point, and you have to fit your your intercept, your slope, and also technically your variance. But we'll make things easy and say that the variance is like very small here. All right, but still you need both your slope and your intercept, right? So like here's one for you. Here's a line that goes through it. Works pretty fine, right? But here's another one. Let me use the one that you can actually see. There you go. All right, but this one's also valid, and so is this one. And heck, I can go all the way down at like negative infinity and come up as long as I pass through the point, it's fine. All right? So pretty much like almost any line works. So how on earth are we ever going to do this? Well, luckily, you have to remember that with Bayesian statistics, you have your prior and you have your data, right? And your data helps you update your prior to get your posterior. So what happens that you can actually imagine that in a Bayesian approach, you can actually have no data and you're fine. All that's going to happen is you say the probability of our theta given our data has to be proportional to the probability of the data given our theta times our prior, right? If I tell you, hey, I'm giving you no data, then what's my posterior going to be? Well, in that case, the posterior will just be equal to my prior because I have no data. So how am I going to update? There's nothing to update with. I'm just back to my prior. So what we're going to end up with here is we're going to start with some prior for our slope and intercept. And this data will somehow help us update somewhat, right? Now, clearly, it's not going to be able to help us out very much because, practically any alpha and beta work as long as it passes through this 0.11, right? But you can update nonetheless, right? There's nothing stopping you here in the Bayesian approach. Absolutely fine. We just need to set our priors, and we're good to go. And we have to set our priors every time anyway. So now, as I get into it, there's going to be some more nuance to it. There will be some nuance. Don't worry, because obviously there's something up here. But what we'll see is that you can fit it. There's nothing wrong conceptually with fitting it, and there's nothing wrong technically with fitting it. Although I will say that the computer cries a little bit when you do it. You'll see. But you can fit it. How you interpret things, and also how you actually do it in practice, where you have to be very careful about your priors, is what we'll find out. How you interpret these results, that's where things get a little bit tricky. But there's nothing in Bayesian statistics that'll stop you from fitting this model. So let's see it. So once again, just because I want to be done in a half an hour, I'll speed it up by copying some code over that I've already written. So it's exactly what you kind of expect here. Let me see here. I got to clean things up a little bit once I copy it over. So here we go. What I'm going to do here is I got rid of my, let's do it just with 2 and let's just do it with 1 and 1, kind of our standard here. Well, let me make it be 2 and 2 for our alpha and beta here, right? And then what I've done is I set it up so that way our point here, usually we say alpha plus beta times x. Well, in this case, our x is an array with just a single value of 1. And then for our y's, we have our standard alpha plus beta for our mu there. Our standard deviation, I just said that rather than having a sigma that we estimate, I'm just fixing it to 0.01. I'm just going to say like, okay, we know this point pretty darn well, right? And then finally, you have this, maybe I'll make it be a little bit wider, 0.1. All right, so we know within like 0.1. It could be 0.1 up or down. And then finally, for the observed, we've seen one value, which is a y of 1. And so now we can grab our posterior and take a look at it. So our alpha was between 0 and 2, our beta was between 0 and 2, and mean 0, standard deviation 2. Let's run this real fast, and we'll see what happens. Actually, the sample's okay. When we do some of the later ones, it'll cry more. Don't worry. No divergences, even not bad. Now it does warn us right here. Oh, it's crying a little bit. The effective number of samples is smaller than 25% for some parameters. That's actually something that is quite worrisome in general. I will say that. So that is something to be aware of, and it's going to warn you. And we'll talk about this once we get to week 9, which is effective sample sizes. But essentially, it's a warning that's having a hard time sampling from this distribution, from this posterior. But we get our alpha as promised. We get our beta as promised. They're quite uncertain though, as we'll see, which isn't too big a surprise. So let's quickly plot some of these. Let's plot the joint. Let's plot a posterior first. Plot posterior of, let's say, posterior of alpha. Let's take a look at it. Oh, I'm sorry. Plot posterior. I knew something looked off there. There we go. So here it is. First of all, you'll notice that's not that nice smooth thing, and that's mainly just because it has problems sampling. So this is just a computational error. It really is normal. But you'll see we started off saying, oh yeah, it's somewhere between, say, -2 and 2, and afterwards it's like, yep, it's between -2 and 2, all right. We didn't really get any better estimates out of it. All right, how about for the beta? Did we get any better estimates out of the beta? We said, about one standard deviation was between -2 and 2, and yeah, I mean, they're a little bit higher. But that's about it. Let's look at the let's see here. What else can we plot? We can try plotting the one other thing that was always fun to plot is the lines. We can plot some of the simulated lines on the curve, right? So we can do for I in range of, and I'm going to do it a little bit differently just because this is purely because of the technical side of things. So don't worry about it too much here. 0, 1000, and increments of 20. So rather than plotting 0 to 50, the first 50 lines, I'm going to take every 20th line. And that's the equivalent of doing 50 of them. But it is important to do it a little bit because when it's having problems sampling, you sometimes want to space out the ones that you actually look at. Like I said, I'll explain it in 3 weeks, 3 or 4 weeks. So let's try plotting this though. Plot. We need to plot, we need some x values. So x is equals np dot lens space of, let's see here, we must start at 0, go to, say, let's go to 2, and then we'll have 100 points. And we plot our x's, and then we have to plot our posterior of alpha of I plus posterior of beta of I times our x's. And then we want these to be, say, red, and we want the alpha to be 0.5 or something like that. All right, that should look good. So now we're going to plot 50 of these lines, and this is what they look like. Hey, that's pretty much what we drew on the board, right? So all the lines, they actually go through the 0.11 thereabouts. They have a little bit of leeway because we allowed for a little bit of a sigma there of 0.1, but they all pretty much go through the line, right? Which is better than our prior, because our prior said our alpha and beta could be anything. So it could have been that beta was that alpha was 2 and beta was 1, so it would be going up like this. But no, this one point actually did constrain our alphas and betas, so that way they went through that one point. It did its job. The Bayesian inference works exactly as we expected it to. All right, and now let's actually plot the joint. Plot joint. This is where things get a little bit more interesting. Posterior. Let's take a look at this. This is what it looks like. Now remember, we saw things that were tightly correlated before, up above, in the previous problem, we saw some correlation there, right? Like, hey, those things are correlated. Well, look at this guy. Oof, that is really correlated. That's really correlated. And the reason why is, take a look at this. This is what we know. Based on this one data point, what do we know? Well, we know that when x is equal to 1, y should equal 1. That's like pretty much our only bit of data that we have, right? That, we know that's supposed to be y equals alpha plus beta x. And here we know that at 1, it should be equal to 1, right? Thereabouts. And yeah, there's a little bit of a sigma there. If I turn the sigma even more down, like, it has to go right through this point. And maybe I'll do that just to show you. So in this case, what happens here? Alpha has to equal, well, I mean, so you can say that, okay, well, alpha plus beta equals 1. Or alternatively, that alpha has to equal beta, 1 minus beta. Right? And so pretty much they have to be right on this one line. Alpha equals 1 minus beta. And here, let me actually run this again with a smaller standard deviation, and you'll see it where this this kind of line here with a little bit of thick line, it gets thinner and thinner. The more certain we are, it has to go through the 0.01. Let's see here. Where is it? Right here. So let me add in a 0 here and rerun it real fast, just to make a point of this. And already you're starting to see it starting to do it slower. That's because what happens is that as this thing becomes more and more correlated, and gets flatter and flatter, pretty much it has a really hard time sampling from it. That distribution just proves to be really difficult. It's going to condense all the way down to this one line of 1 minus alpha. And so it's actually it's just a slow job sampling from this already. And then don't worry, we're going to make it even harder on it soon. It's really bad once you start seeing these divergences. It says 0 divergences. Once that starts shooting up, then you're in really deep trouble. That's when you know you have a bad model. And in general, when you see something like this, where of course when you have large data sets, it takes a while to sample. But in general, if you start having these lots and lots of warnings and lots of problems with sampling, the rule of thumb is that you screwed up somewhere in your model. It's rarely the software that's screwing up. Like, oh, you did something, you set up the model just right, and it just doesn't know what it's doing with sampling. No, almost every single time it's you've screwed up in writing your model, and it does not like what you've done. And so let's see this here. This is still pretty much going to be the same thing. And they all look a little bit wobbly because of everything. Now this line, they should go more reliably through the point. Wow, they go through it really well now that I've turned down the sigma. And now let's look at this posterior. Now it's pretty much all along a straight line. All right. And this is called multicollinearity. In general, the idea of it is, or well, not quite more or less, where these things are so correlated that they're perfectly correlated, this alpha and beta. And in this case, what you actually have, this isn't quite multicollinearity, but it's the problem of non-identifiability is what it says. Because the problem is this, is that with the data you have, you cannot uniquely determine alpha and beta. You can't get an estimate for alpha and an estimate for beta. What happens is that you can only know a property about the two of them together, right? So in this case, what we know is that alpha plus beta equals 1, but we can't actually get it down to alpha equals this estimate, like our mean or whatever, and beta is equal to the slope. We can't quite get that. We just get that they're a combination of the two. To make this more clear, let me give you one other model, which is actually the multicollinearity problem that is a really good example of it. Suppose I did something else that's kind of, once again, another kind of weird model that you wouldn't normally think of doing. What if I said y is equal to some, now suppose at this time I actually have lots of points, right? Suppose I have a bunch of points here, right? And I say y equals alpha plus beta x, right? And I could easily fit a line, right? But what happens if I said instead, I still have all those points, but instead of this normal model, I'm going to do this, beta 1x plus beta 2x. We can run this model, it will also work. The computer will really hate sampling from it, but it can absolutely do it. Beta 2x. X. So what's going on here? This is a weird one. All right. This one's a weird one. Let's actually do it. Let's do it. This is actually such a cool problem. Let's do it, and we'll see what happens here. All right. I'm going to quickly do a detour and actually try to run this model, because you'll see that this is a weird model. I'll do it quickly so that way I'm still done in the, oh, geez, 20 minutes, 15 minutes I have left. All right. All right. We'll do it. We'll do it. We'll do it. I'll somehow do it. I don't know. I may show you. There's only a couple things we need to talk about. So let's suppose we generate some x's and y's really fast. We're going to come back to this alpha beta problem in just a moment. All right, but suppose I generate some 20 x's, have some y's, which are 6x plus 3, right? Very simple model here. And then let's quickly fit it using first a standard model, and then we'll do this more messed up one with the betas here. So we'll allow for the sigma there. Let's do this thing. Let's just have one beta, This is just a standard model here. So we can run this and it should estimate just fine. az.summary of posterior. And sure enough, it says, yeah, your alpha is somewhere between 2 and 3. It turned out to be 3, and then the slope was 5 to 5.5, 6.5, and it was actually 6. So it does a just a fine job. And sigma was 1, and it estimates, somewhere around 1. So it does a great job. Now let's beat it up and give it to the beta 1 and the beta 2. This is a fun one. And just for the sake of argument here, let's give these wide priors. All right, suppose I didn't have much in the way of priors. What's going to happen here? Plus beta 2 times x's. And now we run this one, and trust me, it's going really slow, and I'll explain on the board what's going to happen here. All right, it's running. We'll let it run for a little bit. It's probably going to take like 2 or 3 minutes. All right. If we look at this, the problem is that what's it going to do here? Right? The x's are the same. So you can actually rewrite this as saying it's going to be equal to alpha plus beta 1 plus beta 2 times x, just by pulling out the x there. And now we know that the slope for the original one was 6. So it has to figure out that beta 1 plus beta 2 is equal to 6, right? Like we know together with our data that it should be 6. But all it knows is that beta 1 plus beta 2 is equal to 6. It doesn't actually know it can't tell which one's which, right? Because what you could do is, you could say beta 1, let's do a little table here, beta 1, beta 2. You could say, okay, beta 1 is 5, beta 2 is 1, right? That'll add up to 6. You can say beta 2 is, say, 3 and 3. You can do 1 and 5. You can do minus 100 and 106. This is all valid, right? As long as the two add up to 6, they're fine betas, right? And then at the end of the day, it's going to make the same prediction, right? Because it's going to be like alpha minus 100x plus 106x. Well, that's just plus 6x, right? And so you can actually do anything you want here. So what's stopping it from plugging in, say, 1,000,000? I'm not going to actually do 1,000,000 because I'm too lazy to write it all. And 10,006, right? What's actually stopping this? The only thing stopping this is our prior, right? Because remember, we say down here that our prior is that beta 1 and beta 2, or for example, both distributed normally about, say, 0 and 10, or 0 and 100. So now, while these are all okay because they're all within about 1 standard deviation, this guy is so far out of there, for a beta where we say it's only can go up to, say, like 200-ish, right? 2 standard deviations away. 10,000, we're like, our prior says that's just not the case, right? Now, if we kept upping up our prior to like 10,000 or 1,000,000, then all of these would be okay. And yeah, it would have to say, well, minus 10,000 plus 10,006 or is a perfectly fair set for alpha for beta 1 and beta 2. Our priors are the only things keeping this from allowing anything from negative infinity to infinity. If we didn't have priors, and the weaker our priors, these values can take anything. Just like with that alpha, with the slope and intercept, it has to go through 1, 1. Based on our prior, the wider our priors, we would keep going up higher and higher on a steeper slope to get down and still hit 1. It's only our priors saying that alpha and beta are, say, between 0 and 10 or so that's keeping it from going wild, way up there. And so the weaker your priors, the weaker your posteriors in this case. We always say that, oh yeah, well, no matter what your prior for a lot of these things with lots of data, the data will overwhelm it and you're going to get some consistent prior. With these, not so a really nice posterior, regardless of how wide your prior is. In this case, not the case. Whatever you choose for your prior is going to dictate what your posterior is because there's just not enough data to narrow it down. So let's take a look at this. So now it's not so pleasant here. It is you can see it had divergences now. I warned about that. And they say, uh-oh, there were divergences here. That's not good. The acceptance probability is not good. Estimated number of effective samples are smaller than 200 for some parameters. That's a disaster. And now we look at it, our betas can go from minus 111 up to 120, or minus 113 all the way up to 117. Oh no, look at this. These betas are a disaster, right? So here we can try doing plot the posterior, for example. Az.plot posterior of, let's do posterior of beta 1. Let's do it. Let's look at this. Oh no, it is anywhere from minus 100 to 100. All right, I mean, here, let's quickly add on our prior onto this real fast, because I think that's interesting to show you how our prior and our posterior is pretty much identical to our original prior. It's very sad to see. Let me see if I can pull this up real fast. Here we go. What was our prior for this guy? Let me see here. It was 0, 100. Let's go from minus 200 to 200, and then we'll do 100 points. That's fine. We'll plot our beta 1, and then I need to plot something a little bit different here. I just want to actually plot the prior for beta 1. So in this case, we're going to plot our x's and a normal PDF centered on 0, scale of 100. So let's see it. So that's our prior. Goes pretty wide, and our posterior is pretty much the same. It's actually a little bit off from the extremes there, which is nice. But it clearly hasn't gotten much better from where it started. Not better at all, really. There's almost no information. Compared to when you think of something else where you get these really nice tight posteriors, the prior's not really added much. Now here's what's interesting though. What if we were to add together the beta 1 and beta 2s? So let's see this. Az.plot posterior, not plot posterior, plot joint. It helps if I can spell plot. Of the posterior, var names equals beta 1, beta 2. So if we plot this, we're going to see once again, we got our multicollinearity, right? Perfectly correlated. So here, take a look at this. Now let's do posterior of beta 1 plus posterior of beta 2. Let's add up the samples. What are we going to get? Look at that. They're all centered close to 6, which was our original estimate. All right, let's do this. Az.plot posterior of the sum of the two. For that one, even though they vary wildly, they go from minus 100 to a 100. Oops, minus 100 up to 100. Right? When you add the two numbers together, because every time this one's minus 200, the other one is 206. Every time this one's 200, the other one is minus 194 or whatnot. And whenever this one's 0, the other one's 6. When you add them up, look at that. They're almost always right around 6. It gets the perfect estimate to the slope and has pretty tight uncertainty. It's between 5.4 and 6.6 is our slope estimate, which is what we had when we did it the normal way up above, which I think I deleted. Oh, well. Right? So we're still getting the same results at the end of the day. We can still add the two together and we get exactly the same result because, the model's the same. It just now has two betas instead of one, but when you add them together, it has to be the original beta, right? So it hasn't screwed up anything. Bayesian inference works exactly as it was supposed to. It's just that now we have these two parameters that we can't really figure out what they're supposed to be. We just know that their sum is supposed to be 6. So that's why this line right here is the line x plus beta 1 plus beta 2 equals 6. If we zoomed in, you would see it goes right through 6, 0, 0, 6, and 3, 3. It passes right through them if we zoomed in. It's just that the problem is that we just can't really tell you what beta 1 or beta 2 is individually. There's just not enough information to tell. Now, why is it worth talking about all this multicollinearity business? Well, it turns out that when you actually sit down and you're doing theoretical models, you very frequently you frequently create non-identifiable models, whether you mean to or not. This is a very common problem in macroeconomics, especially, but it happens in a lot of different places. And when you do it, you can accidentally make bad decisions in how you handle it. So, and that's because suppose that I told you what I was actually interested in out of everything was, for example, up here, the thing I was interested in was the slope, right? Well, the slope depends on what my prior was, right? Because I can't actually get the slope out of this. The only thing I can really tell out of this data is that it passes through the point 1, right? And that the sum of the slope and alpha have to be 1 or whatever I think I said it was. I think alpha plus beta had to be equal 1 here. So I can tell you that much. But if you ask me what beta is, what the slope is, I don't know, right? If I had a really large prior to begin with, my prior was very wide. Right now, in this case, it was only 0, 2. But if it was 0, 200, well, then my beta could be anything from plus 200 to minus 200. I don't know which one it is. It could be anything in between. If my prior was 10 million, then now my beta could be anything from minus 10 million to 10 million. Everything depends on the prior because I don't have enough data to tell you otherwise. And so that's a dangerous spot to be in if you start trying to report on your beta. Because your beta right now, is not dependent on your data, it depends more on your prior. And so something that happened was actually a few years ago, Paul Romer, who is a guy who's a Nobel laureate in macroeconomics, he wrote this paper called The Trouble with Macroeconomics. This is only a few years back, as you can see. And he was arguing that, the entire field is in trouble. And the reason why is because the treatment of identification now is no more credible than in the 1970s. But they've made it more opaque. And he starts talking about the fact that the way that is that a lot of their models have non-identification where they can't actually get the specific parameters, right? They can't actually estimate them. And so the only way they can do it is by making assumptions. And what he says, those assumptions are often just crazy and bad, right? And that they don't actually justify those very well. And so what he says here is that identification problem means that to get results, an econometrician has to feed in something other than data on the variables in the simultaneous system, right? If you have the alpha and beta, you can't tell what it is based on the data. You have to feed in some other assumption, like your priors or something, in order to actually get estimates, right? That's the only way you can. And so he calls these assumptions, I call them assumption. He calls them, in this case, facts with unknown truth value. Because to emphasize that although the estimation process treats them as if they were facts known to be true, the process of estimating the model reveals nothing about the truth value. So if we sit there and assume ahead of time that the alpha is between 0 and 1, then the posterior is going to say it's between 0 and 1. The model assumes it to be true, but it doesn't actually verify that it is, right? We don't know we have to actually put in real priors based on what we know what the alpha should actually be. We can't just put in some random alpha because our model isn't going to actually be able to tell us anything more precise when it's fitting it. And he calls out Bayesian in particular, and we'll get to the point on where he ends up calling out betas down on Bayesian stuff once we get to later in page 14 here, where he says, he's trying to show some modeling stuff, and he says, but there's also, so in classical statistics, they have to make these assumptions where they set parameters like, oh, we're going to set alpha to 0. And he says, to replicate the results that this one paper had done, I used the user guide because he's not a Bayesian. And he goes, in listing the advantages of Bayesian approach, the user guide said, third, the inclusion of priors helps identify parameters. So this was a revelation. Being a Bayesian means that your software never barfs. So like I said, if we tried to fit one of these alpha beta thing, with a single point, most regression softwares would barf, right? They would say error, we can't do this, you only have 1 point. But with a Bayesian, because we have our priors, it'll still run, right? And so the point for this people who are doing some of these macroeconomic models using Bayesian approaches, they say, hey, you can help identify some of your parameters by setting priors on them that are reasonable is the idea. and you get reasonable estimates on what you think the posterior is for the other one. Now, of course, once you've set your priors, you have to trust your priors, but once you do it, you'll at least get the information that you can out of the model. It'll do the best it can given your priors and the data that is there, even if it's limited. All right. So he said, in retrospect, this should have been easier to see. He says, assuming something is exactly zero is very equivalent to setting a type prior. And so he says, what's interesting, now this is where his complaint is. It's very interesting. What he says is that what you can do is, let's say that I'm actually interested in the slope. What he says is, suppose that I do a Bayesian estimate where I set a type prior on my alpha. Say the alpha, I'm pretty sure it's close to zero. Then, regardless of my prior for the beta, it's going to end up having to go through 1. And so I'll show you how this works. It's a very interesting thing that he points out here. And it's a very legitimate complaint that if you're not careful with your Bayesian process and model, you could end up fooling yourself into thinking that you actually have more information in your model than you really do. And so what he says is, okay, let me do it here. So before we had this, right, where we have no idea what the beta is, we have no idea what the alpha is, right? It's the same as our prior pretty much. What he says is, suppose that some unscrupulous person sets their alpha to be, they say, oh, well, the intercept, I think is close to zero, right? And they don't really have a true justification for it, but they're just going to set it to zero. But the beta, I genuinely, I don't know that, I'm going to set it to be 100. So I have like maybe I'll do it to 10 just for effect here, right? I really don't know for sure, but the beta, I'm pretty sure that the alpha, I'm pretty sure that one's close to zero. And now you run your model. It samples okay. It's not giving us really any errors, right? So we started off with a prior of our beta where it was 10 for our standard deviation, but our alpha we inappropriately set to a small prior, right? And what ends up happening is that we get that the alpha is pretty much the same, right? We said it was plus or minus 0.1, and it's like, yeah, it's 0 plus or minus 0.1. But our beta, where we said it could be minus 10 to 10 or minus 20 to 20, somewhere in there, it says, your posterior it's 1. And it's pretty darn tight there, right? It's plus or minus 0.15 around 1. And so here, let's take a look at this. Let's look at our priors and our posterior and compare them real fast. Here we go. Let's see here. I'm just going to paste this right in here. So here in blue is our posterior for our alpha. Red is our prior. Pretty much unchanged. So what we were saying is, yeah, the model can't really identify. It can't really get any better than what we started with, right? We didn't get any extra information about the beta, about the alpha. But now let's look at the beta. What's that look like? Here was our prior. It was really flat. We had no idea. And this is our posterior, really tight. So now, if you're not careful, you could say, look at this. With the data in the model, we were able to get a tight estimate on the for our beta, even though we had a weak prior on it, right? And so it's all good, right? We got our estimate for beta, which we wanted, right? And that's because, look at this. The line, it looks pretty good. But we know that the only reason why we were able to get a tight fit on this was because we put a tight prior on alpha. If we go back to what we had before, where alpha was, say, 5, and suddenly we're back to the problem of getting weak estimates. And you're going to see that the beta is now, I'll let it run for a minute, but the beta is back to not knowing it. The only reason why we actually had a tight posterior on beta was because we put the tight posterior on alpha. Once we said, we know it goes through 1, 1, and now we said, and we know it goes through 0, we set our alpha to be 0, now you've defined the line. The only reason you were able to get a strong estimate for the slope was because you set a prior on the alpha. So what he says here, he describes exactly this. So in the jargon, I could say that, so he says, okay, if I do this, the Bayesian procedure will show that the posterior of the intercept for the supply curve is close to the prior distribution that I fed in, that I feed in, which is exactly what we saw. So in the jargon, I could say the data are not informative about the value of the intercept of the supply curve. But then I could say the slope of the demand curve, the slope here, the beta, has a tight posterior that's different from its prior. By omission, the reader could infer that it is the data as captured in the likelihood function that are informative about the elasticity of the demand curve, when in fact it is the prior on the intercept of the supply curve that pins it down and yields the tight posterior. By changing the priors I feed into the supply curve, I can change the posteriors I get out. Right? I could change that prior if I say, oh, actually, I think the prior is that the alpha is on 1. Now my slope has to be flat. It has to be 0. And he says, this was news to me. But once I understood it and I started to be careful, I realized this was an open secret among econometricians. In the paper with the title that I note in the introduction, Canova and Sala write that uncritical use of Bayesian methods, including employing prior distributions which do not truly reflect spread uncertainty, may hide identification pathologies, where you're making key assumptions, even though because you're using priors that don't actually reflect your true uncertainty. Other people show that if you feed different priors into certain people's models, you get back different estimates to the key parameters that they're trying to estimate. And other ones, they note that without any information from priors, the model is not identified. They echo it. And so you got to be really careful. You got to be really careful when you do this stuff. And so right now it's still running. It's almost done. We'll see it right here. Just changing the prior on alpha here will dramatically change my conclusion for beta. Right? Oh, I plotted this thing a little bit wrong here. Because now that we have a larger prior here, let me do this from minus, what I say, minus 10 to 10. Not that this matters, this is just for alpha, which, once again, there's not really anything in there. I think I set 5 for it now. Yeah, it's all messed up because I had problem, that's a sorry looking sampling, right? But whatever, and now look at the beta. Now it's like, I don't know what I am anymore. I'm anything, no idea what it is anymore, right? Thanks to the damage of setting a larger prior on it. And, by changing the prior on the alpha, it has ruined our posterior and our beta. Not a surprise. All right. It's not nice and tight like it was before. Now that we just changed that. And so this is something you need to be careful about. When you have non-identified models, you got to be really careful with your priors. Very careful. All right. And I wanted to do it. I want to do one more thing, but it's already 2 1.5-hour lectures, so I'm just going to call it quits here. In class, we'll go over a cool one, which is a actual theoretical model where we estimate the person's weight based on their height. And what you'll see is that just in the normal course of trying to build a model, it ends up being non-identifiable. And so you'll have to be careful with the priors when we do it. And then I'll also talk to you guys about in class, I'll talk to you guys about, there's actually a cool COVID model, Bayesian COVID model by people out of UC Irvine, and they, and in it though, their COVID model ends up being non-identifiable at a couple parts. At least they suspect it is. And you'll see that pretty much their posterior matches their prior exactly on a couple of the key parameters of their theoretical model. But it's a cool model to go through and show you kind of how people do it in real life situations. All right. So I'll leave it there. And then I will see you guys in class.